Hi, this presentation is on introduction to vectors. What is a vector? A vector is a quantity that has both magnitude and direction. Some of the characteristics of a vector are a vector has an initial point, or it's called the tail. A vector has terminal point, or it is also called the tip. Now we said a vector is a quantity that has both magnitude and direction. So magnitude, that's another characteristic of the vector. So what is a magnitude? It is the length of the line segment connecting the initial point and the tail. So we're talking about the length of uh, this this segment. So it's a line segment connecting the initial point and the terminal point, or the tail and the tip. That would be the magnitude. So what do we really mean by that? Example, if this vector represents some force applied on some object, and let's say this force is 20 newtons, 20 newtons. Now we can divide, this is just an example, divide this vector segment into four equal segments, and each segment we said is 1 unit. That means each 1 unit is 5 newtons. So 5, 5, 5, 5, that's 20. So it means the four segments, that's the length of the vector, and what that represents is 20 newtons. Each segment, 5 newtons. All right, that's in regards to the magnitude. Let's talk about the direction. So a vector has also direction. What is the direction? If you look at this figure over here, so we can see that there is an angle of 35 degrees. So let's talk about that. So direction is what? It is the angle of rotation the vector makes with its initial position. So this would be the initial position, and this is the terminal position of the vector, and this would be the angle of rotation. In this case, it's 35 degrees. So let me finish reading this. So in the figure above, the direction is the angle between the vector and the horizontal line, which is the x-axis in this case. Doesn't have to always be the x-axis, but we will be actually working with vectors on the xy plane. So we will the initial point will always be the x-axis, but it doesn't have to be. All right, so we talked so far about the magnitude of the vector, direction of the vector. Let's talk about standard position, which this term standard position sound familiar. We went over this when we worked on trigonometry, and we talked about standard position in trigonometry. So a vector, we say that a vector is in standard position if the initial point of the vector is at the origin. If the initial point of the vector is at the origin. Let me start to remove this. No, it's okay. Okay, worked. Finally, good. So, okay. This is the initial point. So if the initial point of the vector is at the origin, then we can say that this vector is in standard position. So far, we're getting familiar with the terminology and vector representation. Example, let's talk a bit about some examples where we can say, okay, well, that's an example of a vector, that's an example of not a vector, and so on. So, what does the example ask us to do? State whether each quantity described is a vector quantity or scalar quantity. So, we have already introduced what a vector quantity is. We said it is the it's a quantity that has both magnitude and direction. So vector is a quantity that has both uh, the magnitude and direction. So what is a scalar? A scalar would just have the magnitude, no direction. That's the difference between the two. Okay. Example 1a, a car traveling 60 miles per hour. That would be magnitude. Magnitude. And then 15 degrees east of south. That's direction. So what is this? Vector. Good. Let's move on to example B. A child pulling a sled with a force of 40 newtons. That's a magnitude. What is the direction? I don't see it. We don't have the direction. We don't know which direction is this sled being pulled. Is it being pulled north, south, east, west, left, right, down, up? We have no idea. So for that reason, this is a scalar. This is a scalar, not a vector. Example C, a parachutist falling straight down direction. That's direction. At 12.5 miles per hour magnitude. Conclusion, vector. Good. Let's move on to types of vectors. What we mean by types of vectors is more of the how the vectors relate to each other. Okay, so we're going to start with the first one, which is parallel vectors. It's like talking about parallel lines. So when do we say that two vectors are parallel, or more than two, 3, 4, 5, 10, 100, if they have the same or opposite direction? The same direction or opposite direction, but they don't have to have the same magnitude. They don't need to have the same magnitude. Um, so they must have the same direction or opposite, but not necessarily the same magnitude. So let's look at the figure and determine which vectors are parallel. So let's start with vector A. So that's second. So vector A is parallel to vector B because they have the same direction. They don't have to have same magnitude. So it is parallel to vector B. It is parallel to vector C, got the same direction. It is parallel to vector E. See, vector A and vector E have opposite directions. So still, they are parallel. Vector F also parallel. And also all these vectors are parallel to each other. So vector C is parallel to E, and C to F, and E to F, and so on, and B to C, and B to E, and B to F. So all these vectors are parallel to each other. So all right, so that's parallel vectors. So now let's talk about equivalent vectors. Equivalent vectors. Equivalent vectors, they have the same magnitude. So equivalent vectors have the same magnitude and direction. So same direction and equivalent and the same magnitude, meaning equal magnitude. All right. Which two vectors have the same magnitude and direction? Let's take a look. So if we compare vector A to compare B, well, they have the same direction, but not the same magnitude. So they're not equivalent. It looks like vector A and C, they have the same um, direction and magnitude. Actually, these are the only two that they have the same direction and same magnitude. Vector A and vector C. Okay, so A and C, so let's write them down. So A is equivalent to C. Now, is here what I put over here is A is not equivalent to B. Let's take a look. A is not equivalent to B because they don't have the same magnitude. See, B is longer than A. Since the magnitude of A does not equal the magnitude of B. This absolute value borrows mean magnitude in here. So also A is not equivalent to D. A and D. So they have the same magnitude, but they don't have the same direction. They don't have the same. So since A and D do not have the same direction, so they're not equivalent. And there are more non-equivalent examples. Now the last thing will be opposite vectors. Opposite vectors um, would have the same magnitude but opposite direction. Same magnitude, opposite direction. Um, we can come up with a vector that is opposite to itself. So let's say a vector A, the opposite of A will be negative A, meaning we can create another vector, we name it the same thing with the letter A, but we put negative A, that means the opposite. So the vector opposite A is written as negative A. So, but let's look at our figure and see which two vectors are opposite vectors. So to me, it looks like vector A and vector E are opposite vectors. Okay, opposite vectors. They got opposite direction. Same magnitude, opposite direction. These are the only two that they have the same magnitude and opposite direction. Or probably there is more. We'll see. Yeah, more. Sorry. So A and E, also C and E. So A and E and C and E, they have opposite direction. So they are opposite vectors. So we're going to say um, A equals negative E. Let me make sure I'm writing the right thing. Yeah, A equals negative E and C equals negative E. And C equals negative E. So what do I mean by A equals negative E? So let me explain. This is A. And initially, before I make a change to E, this would be E. Okay. Now, if I negate the E, if I negate it, multiply it by negative, then what happens? The direction will change. This is negative E. Now look, vector A and E, they have the same direction. I mean, negative E have the same direction. They were opposite vectors. If they are opposite vectors, it means one equals the negative of the other. To turn them into equivalent vectors, the only way to do that is to multiply one of them by a negative. We could have done E equals negative A, that's fine. And E equals negative C, that's fine. Um, Either way is correct. Okay, let's move on to the next concept, which is uh, how to add vectors. how to add vectors, like how to add real numbers. Now we're going to learn how to add vectors. Of course, when we add vectors, there are two things: how we can use geometry to add vectors, and how to add vectors in regards to adding their magnitude, actually, which we're going to talk about that later on. So let's start. When two or more vectors are added, their sum is a single vector called the resultant. So it means we have two vectors initially, we add these two vectors, we end up with one vector. What do we call this vector? Resultant vector. It's like adding two real numbers, you end up with one real number or one number. Now, geometrically, the resultant can be found using either the triangle method or the parallelogram method. So these are the two different methods um, to add vectors geometrically. All right, let's start with the triangle method. The triangle method is also called tip to tail, or how it works really is tip to tail. So what does it mean? Okay, what does that mean? Um, all right, I'm gonna draw it over here separately. So here's vector B, and here's vector A. I try to replicate this figure to the best of my ability. Okay, replicate this. Okay, not bad. Okay, so vector A, vector B. So the triangle method says you gotta connect the tip to the tail. So it means we have to translate vector A and connect the tip of vector A to the tail of vector B. Or you can translate vector B, connect the tip of vector B to the tail of vector A. So I'm going to go the easy way, which is what? The tip of vector A to the tail of vector B. So I'm going to erase this, just attach it. Okay, so now we have first step is done, maybe a bit longer. Now the second step is the resultant vector. So what is a resultant vector? Is a vector that connects the tail of vector A and the tip of vector B. This is how we add these two vectors. So let's call this a resultant vector R. So it means when we add A plus B, the vector that we get will be the vector R. This is called the triangle method or tip to tail method. Now we can add the same two vectors using different method, which is called the parallelogram method. Tail to tail, meaning we're going to attach the tail of vector A to the tail of vector B. So let's do that. And the resultant vector should be the same. Doesn't matter which method we use, whether we use triangle method or parallelogram method, the resultant vector will be the same. Okay, so let me replicate this figure. This is vector B. And then what the question, I mean, what the method says, connect the tail of one of the vectors to the tail of the other vector. So that now it's up to you what you want to do, or it's up to us. We can connect the tail, we can translate vector A, or we can translate vector B. Let's just translate vector A. So if we translate vector A, we have to, or actually in this case, translating probably the vector. Let me see which one is better. Actually, doesn't really matter. Um, okay, yeah, I want to do this instead. Okay, so um, let's replicate vector A. This is A. I'm going to translate vector B. All right, here's vector B. Translate it. So may not be perfect, but I try. Okay. All right, so this is vector B. Now, both tails are connected. So what I'm going to do next, I'm going to have to draw or replicate vector B starting from the tip of vector A, like this. Use dashed lines so we differentiate between the two. So that's a replicate of vector B. And then I do the same thing for vector A. I'm gonna replicate it but starting from the tip of vector B, like that. Good. Finally, now what we can do, now we can connect, now we can draw the resultant vector. So the resultant vector would go from the tail of both vectors to the tip of both vectors, but the replicas, of course. So it's like drawing a rectangle. Sorry, parallelogram. That's why it's called parallelogram, not a rectangle, parallelogram. So we kind of that's why it's called parallelogram method. Pretty much we draw parallelogram here, and then we connect the uh, opposite corners, but gotta be from the tail to the tip of the dashed line vectors. And as you see, this resultant vector um, is the same as that resultant vector. Maybe it looks longer here because um, because you know I'm not probably as precise. Not the scale is off a little bit, but in reality, it is the same. All right. Next concept will be multiplying a vector by a scalar. Multiplying a vector by a scalar. Multiplying a vector by a scalar, meaning multiplying a vector by some number, and that, of course, changes the magnitude of the vector, but also can change the direction of the vector. So, for instance, if uh, this is vector A, and let's say the magnitude of vector A is let's make it a bit smaller. So this is vector A. Let's say the magnitude of vector A is 1. Let's just put 1. Okay, magnitude is 1. Or well, let's do this. So the magnitude of A is 1. Okay. Now, if I multiply this vector by 2, right, it becomes 2A. Okay, 2 times A. If I multiply this vector by 2, 2 times A. What I did is I multiplied the magnitude of this vector by 2. As you see over here, if a vector v, let me read this, if a vector v is multiplied by a real number k, the scalar multiple k times v, so that number times a vector, has a magnitude of the absolute value of k times the magnitude is absolute value of k times the magnitude of v. So it means if I write 2a, that means I multiplied 2 by the magnitude of a, which is 2. Magnitude of a is 1, so it's 2. So if the magnitude of this vector became 2, then it means the length of this vector will double. So vector A becomes double in length. Now, how about if I multiply the same vector, but by negative 2? So I'm going to multiply it by negative 2. So negative 2a. So the magnitude of the vector A, the magnitude, it would be absolute value of negative 2 times the magnitude of A, which is negative, uh, I'm sorry, 2 times 1, which is 2. Well, the magnitude is still 2. However, that negative will change the direction of vector A. So the new vector in this case, the resultant vector in this case, it will be this one. Double in magnitude is too long. So it's twice vector A, but opposite direction. Okay, so this is negative 2A. I hope this is clear. Let me read these two bullet points. If k is positive, it means if the number or the scalar uh, that is that we multiply the vector v by is positive, then the resultant vector would have the same direction as v. If the scalar is negative, and then k times v has the opposite direction as v, as I showed you here with the vector a. All right. Finally, let's look at vector applications, which is kind of the our objective. Vector applications. It means how we can use vectors to solve problems. Now, um, vector addition and trigonometry can be used to solve vector problems involving triangles. So that means in some applications, we can use vector addition and the knowledge of trigonometry combined together to solve some uh, word problems, or in some applications, we can use vector addition and trigonometry to solve these problems. And of course, if the trigonometry is involved, then triangles are involved. All right, let's look at example 2. Example 2 says Heather is pushing the handle of a lawn mower with a force of 450 newtons. That's the magnitude. At an angle of 56 degrees, that's the direction. And the picture says it all. So I think the problem is clear. So we got Heather pushing the handle of a lawnmower with a force of 450 Newton at an angle of 56 degrees with the ground. Now, if we apply this type of force on the lawnmower, then obviously this lawnmower will move forward. We also um, push it down as well, make more contact with the ground. Okay, the first question says draw a diagram that shows the resolution of the force that Heather exerts into its rectangular components. So let's see what we're talking about over here. Here's Heather's force. So Heather's force is this one, 450 Newton. This is Heather's force. Now, as she pushes the handle, the mower will move forward. It means that this force splits into a horizontal component. We call it component, horizontal component. Let's use blue color. So as if she's pushing forward, but let's put it here. Okay, so the mower moves forward, so that's the horizontal component. Also, it is the lawnmower is also pushed down, and that's the vertical component. So let's use another color. Let's use orange. All right, down. Let's label this with Y, and let's label the horizontal one with X. This is 90 degrees. This is still 56 degrees. So now, as you see, um, the resolution is the 450 newtons vector, the green one. That's the resolution. This resolution vector has two components, horizontal component, vertical component. All right, that's the answer to question A. Now, question B it says find the magnitude. Find the magnitude. So we're gonna have to underline find the magnitude of the horizontal and vertical components of the force. Meaning, what is the magnitude of x? What is the magnitude of y? Well, we can use trigonometry here to determine the magnitude of x and magnitude of y. From that triangle, this is a right triangle. We know that, let's find x first, okay? So let's find x. We know that cosine of 56 degrees is the adjacent, which is x, divided by the hypotenuse, which is 450. Using algebra, we cross multiply. X equals 450 times cosine 56 degrees. Then we can put this in a calculator and determine what 450 times cosine 56. Make sure you go to mode and set the unit, the degree unit to, I mean the angle measure unit to degrees, because the angle is given to us in degrees. After we do that, then we're just gonna multiply 450 times cosine 56, and the answer is 251.637. We're going around to three decimal places, and that's newtons, of course. Now, in regards to the x or the horizontal component, uh, we found its magnitude. Let's do now the vertical component. Let's find the magnitude of the vertical component. So sine 56, sine equals opposite of a hypotenuse. So it's y over 450. So that means y equals 450 times sine 56 degrees. Do the same thing. So 450 times sine 56, the answer is 373.067 newtons. Okay, good. Let's move on to the next example. Next example is very similar to the previous example. So a player kicks a soccer ball so that it leaves the ground with a velocity of 44 feet per second. So that's the magnitude. That's the magnitude. At an angle of 33 degrees, that's the direction where they go. And the picture says it all. Here's the 44 feet per second. That's the velocity of the ball at the instant when it was kicked. And the 33 degrees is the angle made by the resolution vector and the ground. So the first question says, draw a diagram that shows the resolution of this force into its rectangular components. So we're going to do the same thing we did with example 2. First, we draw the resolution vector, which is 44. I mean, this vector, this is the resolution vector, but I just put the magnitude of that vector. So 44 feet. Or let's just put 44. Okay, just put 44. Now it has a horizontal component. Let's call it x. And it has vertical component. Let's call it y. It is a right triangle. And the angle, what is the angle? The angle is 33 degrees. Good. That answers question A. Question B, find the magnitude of the horizontal and vertical components of the velocity. So we do the same thing. We're going to say cosine 33 equals x over 44. You can skip this step if you like to. So x equals 44 cosine 33. And then you do the numerical computation. So 44 cosine 33, that's 36.902 feet per second. Not newtons. Now we have velocity. Sine 33 degrees is the opposite, which is y divided by the hypotenuse, which is 44. That means y equals 44 times sine 33 degrees. Same thing, so 44 sine 33. That gave me 23.964 feet per second. Let me fix this. Feet per second. It's much better. All right. We did find both the magnitude of the horizontal component and the vertical component, and this is the end of this presentation. Thank you for watching.